Hey everybody, Mr. Briz here. So in this lesson, what we're going to do is we're going to have an introduction to differential equations. And then what we're going to do is we're going to solve initial value problems, which we have done before. So that's just going to be a review. And then our last point is that we're going to get into a separable differential equation. So the first part is knowing what a differential equation is. What's interesting is that this is actually a form that's already familiar. It looks a lot like implicit differentiation. So we're going to have a function y of x that also is going to contain its derivative in the equation. So we've got some examples here in the middle. And what I want you to do, before I explain which one is which, I want you to think which of these three is going to be a first order differential equation, and which of them do you suppose will be a second order differential equation? Hopefully what you realize is that first order is talking about the first derivative, and that second order is talking about the second derivative. So I will take the easy way out and just say y double prime. So that means then that if we label these three that we have, the top was a first order, the middle one is a second, and then the bottom is also going to be a first order, because in the first one we have y prime, in the middle one we have y double prime, and in the last one we have y prime. So we've already been doing initial value problems. This one here we have to solve for y. So just remember, we need to integrate both sides, and the antiderivative of y prime is going to take us to y. Then we know that 2x becomes x squared, and sine of x will become minus cosine of x. And then we need to include the plus c. Now we are given an initial value, hence the name. We have y equals pi squared when x is equal to pi. So we should go ahead and put these in. Pi squared equals, and then it'll be another pi squared minus cosine of pi plus c. We need to solve this. I can see that the pi squared on both sides, those will just cancel. So that leaves us with 0 equals, and then if we have to do negative cosine of pi, in the unit circle, cosine of pi is negative 1. And so we are going to get 0 equals 1 plus c, and therefore c will be negative 1. Remember that the last thing that we are supposed to do, the point of an initial value problem, is that we're actually finding an equation for y. So we're going to come back up to this part right here, and we are going to rewrite it as y equals x squared minus cosine of x, and our c value was negative 1. And that's our answer. Okay, in this one then, we are supposed to verify that this equation up at the top is going to be the solution to our initial value problem there. So there's a couple different ways that we could tackle this, and I think the easiest way is if we just happen to find the derivative and the second derivative for that equation there, and then we just verify that the initial values that we were given work for both of them. So the first one is we're given y of 0 equals negative 2, and we already have the equation for y. So let's go ahead and just make a substitution. Negative 2 goes in for y. We're going to have 3 sine of 2 times 0 is going to be 0. And then minus 2 cosine, 2 times 0 again is 0. We know that this first one is just going to be 0. We're left with then negative 2 equals negative 2 times cosine of 0 is 1. And we know that both of those work. So we have verified then that our first part, y of 0 equals negative 2, does indeed work for this function. Then the second part is, let's go find that derivative. Y prime equals, and then we're going to have 6, not sine, but cosine of 2x. And again, the 6 is because we needed to do the chain rule on that. It would have been 3 cosine of 2x times the derivative of the inside is going to be 2. That's why we were going to get 6 cosine 2x. Then the next part, we're going to get minus, actually this will be plus, because it's going to be derivative of cosine is negative sine, and the two negatives will cancel. So we're going to get plus 4 sine of 2x. Then we should take this initial value and put those in. So y prime is supposed to be 6. We get 6 cosine of 2 times 0 is going to be 0, plus 4 times sine of 0. That second part cancels. We're going to get 6 equals 6 times 1, and that is true. So there we have shown that the second initial value that we had is also going to work. All right, now the last part. We have, oh, I already did blue. We have this equation here, and we need to show that that is going to work. So we now need the second derivative. Y double prime is going to be equal to negative 12 sine of 2x. And then it's going to be plus 8 cosine of 2x. Now that we have that, we should just go and put that and y into the equation and check that those will indeed cancel to make 0. So we're going to have then negative 12 sine of 2x plus 8 cosine of 2x. And then for the second part, it was 4 times the original function, 3 sine of 2x minus 2 cosine of 2x. And then that's supposed to be equal to 0. And I can tell that from the first part, negative 12 sine 2x is indeed going to cancel with 4 times 3 sine 2x. 8 cosine of 2x, if we distribute the 4 into there, we're going to get a negative 8 cosine of 2x. That will also cancel. We are going to get 0 equals 0, and therefore we do have this function of y as a solution for our differential equation. So yes. All right, well, I forgot to remove that. I apologize for that. So the variable separable differential equation. What that is going to look like is we're going to have this equation dy over dx equals f of x times g of y. And what we need to do from there is we have to separate this into two parts, hence the name separable. So what I was supposed to have here was that we were going to rewrite as we were going to take the g of y and divide it over to the left side. We were going to take dx and multiply it to the right. And we were going to rewrite this then into 1 over g of y dy equals f of x dx. And then we are supposed to integrate. So the next part was that we would have the integral of 1 over g of y dy equals the integral of f of x dx. And we would just need to solve that. So you are aware, sometimes when we solve these, it's going to be tough for us to get y by itself. So this will be an exception to when I've told you need to get y alone. In these questions, it is okay if you do not simplify, but you need to get the antiderivative on both sides first. So in this case, solve the differential equation dy over dx equals y squared times sine of pi x. So our first step that we are supposed to do is we're supposed to, as the name implies, separate the two variables, x and y. So we're going to divide y squared over to the left side, and we're going to multiply dx to the right. So again, we're taking dx and moving that there. We're going to take y squared and move it there. And there you go. That is our equation after we have separated the two parts. Next, we're going to do the antiderivative on both sides. Over on the left side there, be aware that this is y to the negative 2 power. So when we do the antiderivative of that, sorry, I should maybe keep that. When we do the antiderivative of that, that is going to turn into y to the negative 1 power, and then we have to divide by the new power, so it's become negative y to the negative 1. So that means that over on the left side here, negative y to the negative 1, and then equals, and then over on the right side, the antiderivative of that is going to become negative cosine of pi over x. And we also need to divide by the derivative of the inside. So it's going to be divided by pi. And we do need to remember r plus c. Just so you're aware, on the AP exam, this question has appeared as a free response question several times. It's usually worth a lot of points because they'll give you an initial value too. And believe it or not, they will not award any points if you do not remember to put your integrals on both sides after you have separated it. So, sorry, I phrased that poorly. If you did not separate it, this part is what I should have said. If you don't separate y squared and sine of pi x, the AP exam tells the reader that he or she is not supposed to give any points for that question. And these questions often end up being worth the most in the free response section. A free response, an FRQ is usually, I shouldn't say usually, FRQ is always 9 points, and a question like this is usually around 5 to 6. So that's a lot of points that you would be losing if you don't remember to separate those two parts. Anyway, this here would be acceptable to leave as your answer. If you wanted, you could change it into negative 1 over y equals negative cosine of pi over x, pi times x over pi plus c. You could do that too. Like I said though, it's not really worth trying to get y all by itself here. It's not as easy as just doing the reciprocal. You would actually need to get this part into a single fraction first before you could do the reciprocal. That's just too much work, so we're not going to worry about it. All right, this question, what I want you to do, try this on your own. Once you are done, pause the video first. Once you are done, then you can start the video again, and I will explain how to do it. Okay, now that you have attempted this question, I'm going to demonstrate how to do it. Remember that we need to separate our variables. And one thing that's kind of interesting about this is that we don't have anything for x on the right side. So we do need to move this dx over, but then for the rest of it, there's not really much that we can do. So I'm going to break this into 2 steps just so it's a little easier to see what I'm about to do. We're going to get dy equals 4y minus 1 times dx, but then the 4y minus 1 is the part that's going to move over, not just 4y. We're not allowed to do that. So instead, we need to divide all of 4y minus 1. Now we're going to do the integral of both sides. Over on the left side here, this is going to integrate into natural log. If it is easier, go ahead and do u substitution on it. So we're going to get du is 4 dy. We need to introduce a 4. We also need a 1/4 outside, and that then will allow us to integrate that into 1/4, or not integrate, but substitute into 1/4 times the integral of 1 over u du. Over on the right side, we know that the antiderivative of dx, well, that's a 1 dx, so that's going to turn into x plus c. And then if we do the integral of the left side, that's 1/4 natural log of u equals x plus c. And then we can just substitute in 4y minus 1. And there we go. That is the solution to our initial, oh, I'm sorry, that's a solution, but then we need to do our initial value. So we still need to put 0 in for x and 1/2 in for y. So we will then have 1/4 natural log of 4 times, let's see, 4, I'm sorry, I kind of just lost my train of thought there. 4 times 1/2 minus 1 equals 0 plus c. We're going to get 1/4 natural log of 2 minus 1. That's going to become 1, and that equals c. And we know that natural log of 1 is 0, so we get 0 equals c. We need to substitute this then into our equation that we found earlier. So it turns out that we will have 1/4 natural log of the absolute value of 4y minus 1 equals x. Okay, I chose to include this question as well. This is one of the homework problems that you are supposed to do, but I wanted to show you just because I felt like this might be one that's a little confusing. If you try to separate x and y, initially it looks like it's not going to be possible. So we need to use our exponent rules so that we are able to separate it. We know that dx is going to move to the right side. That's not a problem. But it's trying to figure out how to split up this x minus y as an exponent. That's going to be our problem. So what we need to do, as I said, the exponent rules are going to come into play here. We're going to rewrite e to the x minus y. Whenever we subtract, that was the same as dividing by the same base. So we're going to rewrite our equation like this, and now dx is going to move over to the right side. E to the y is going to move over to the left side. And when we rewrite it, we're going to have e to the y dy is equal to e to the x dx. That's going to be pretty easy to integrate. Over the left side, we have e to the y. Over on the right side, we're going to get e to the x plus c. And that is it. That's all we need to do. This is one where we could actually, you know what, I'm going to go ahead and do that because this is actually a common thing. Differential equations often include e to the x or e to the y. So I'm going to just go one step further and just demonstrate what this is going to look like. We, in order to get y by itself, would have to do the natural log of both sides. And this is going to be helpful for the next video when we do applications of differential equations. So if we have this, then we know that the left side is going to be y, and then over on the right side, natural log of e to the x plus c we can just leave it like that. So it really wasn't that bad trying to solve this. You can have it like that, or if you wanted, you could have left it as e to the y equals e to the x plus c. Either of those would be acceptable, and in fact, I think in the Thomas book, it even leaves it in this second form as your answer. All right, the last thing I wanted to do was just show you a couple more of the questions from the homework. For this, I'm going to admit, the Thomas book, I think, makes this a lot more confusing than what it's supposed to be. This is pretty much just like the first example that we had, where you are just given a differential equation, you're given another equation with y, and you're supposed to check with the initial condition if that is going to work. So we are going to, we're just going to be doing a similar thing here. It's just that it gets phrased really poorly, and therefore it's a lot more difficult than it's supposed to be. So for this first part, I've given you some hints. Show the initial condition works in the solution candidate. So that means then that we're going to take this here and we're just going to put it into the solution candidate equation over there. That means that we're going to get pi over 2 equals e to the negative, well, those negatives cancel, so it'll be e to the natural log of 2, and then the arctangent of 2 times e to the negative natural log of 2. Okay, if we were to simplify this then, we get pi over 2 equals e to the natural log of 2, that's just going to be 2. And then arctangent of 2e to the negative natural log of 2 turns into arctangent of 2 times, well, initially that's going to be 1 over e to the natural log of 2, and then that simplifies even further to become 1/2. And we know then if we continue simplifying, pi over 2 is supposed to be equal to 2. This becomes arctangent of 1. That's where arcsine and arccosine are going to have the same value, and that occurs at pi over 4. So we're going to get 2 times pi over 4. That indeed works. There we go. We have shown for the first part that yes, the initial condition does work. So the second part, I'm going to separate that out here. The second part then is that we are supposed to find the derivative of the solution candidate. And as a hint, I have given you this right here. You are supposed to have that memorized, but just to help you out for right now, the derivative of arctangent, you do need to know that for our Chapter 7 exam. So our derivative of our function is going to be y prime equals, now we have to do product rule, f prime g plus g prime f. So f prime is going to be negative e to the negative x power. Remember your chain rule there, we need the derivative of the exponent. And then it is going to be just arctangent of 2e to the x. And then the second part we need to add, and g prime is going to be, we need the bottom 1 plus, that's 2e to the x squared. And then up on the top, we need the derivative of 2e to the x, which is just 2e to the x. And then we need to multiply by the f function e to the negative x. So that part's a little messy there. I'm going to go ahead and move things around so it's a little cleaner. Okay. And our last thing that we're supposed to do is we have to take this derivative and put it into the differential equation to make sure that everything works out, that we get the same thing on both sides. I noticed for y prime I could have canceled those two right there. So now we're going to put this in. We have negative e to the negative x times arctangent of 2e to the x plus 2 over, I'm going to simplify this, we're going to, when we square this, it's 4e to the 2x. And then we're supposed to do plus the y value, which was given to us as e to the negative x arctangent of 2e to the x. And we're supposed to show that this will be equal to 2 over 1 plus 4e to the 2x. And now we can simplify. I see that this first term is going to cancel with the third term on the left side. And we are left with the exact same thing on both sides. And therefore, that confirms that this worked, this initial value and this equation work for the differential equation. So this is actually just the same question. It was just more room for me, I suppose. So I guess I could have just put this over there. Oh, I don't even think I have enough. I'll have to shrink that down. There we go. Okay, that is everything. So remember, go to Schoology. I've separated this into required questions and optional questions. Also, if you need help, I do encourage you to go to the brief table of integrals